A 2 billion parameter model just beat a 12 billion parameter model, not on some cherry-picked edge case, on multi-turn conversation, the exact thing where bigger models are supposed to dominate. Somebody actually ran the numbers. They benchmarked Gemma 4's E2B variant. That's the 2B model, head-to-head against the 12B version. And the smaller one won. That result has been sitting in a Hacker News thread, getting quietly upvoted by engineers who know what it means. So let's dig into what actually happened here. What it tells us about how we pick models and where this breaks down, because it does break down. Gemma 4 is Google DeepMind's open weight model family. The E2B label stands for 2 billion parameters. For context, most people in 2024 were still assuming that more parameters equals better performance. The 12B model has 6 times the parameters. It should win. It didn't. The benchmark specifically tested multi-turn conversations. That means the model has to remember what was said earlier in the conversation, stay consistent, and build on previous answers without contradicting itself. This is notoriously hard. Longer context, more room to drift, more chances to lose the thread. What the person running this benchmark found was that the 2B model maintained coherence across turns better than the 12B. The scores weren't close. The 2B model held context tighter, gave more consistent follow-up answers, and made fewer factual contradictions within the same conversation. Now here's the thing that makes this actually interesting. This isn't about raw knowledge. The 12B model has more parameters, which generally means more stored information. But multi-turn performance isn't just about knowing things, it's about attention. It's about how the model weighs what came earlier in the conversation against what it's generating now. And apparently, something in how the E2B was trained or structured gives it an edge there specifically. The benchmark also runs on real hardware you might actually use, not A100 clusters. The kind of setup a developer or small team would deploy. And at 2B parameters, the model runs faster, uses less memory, and costs less to serve. So you're not just getting better multi-turn performance, you're getting it cheaper and faster. But let's be honest about what this doesn't tell us. This benchmark is not a comprehensive evaluation. One person ran it, published it on a personal site, and posted it to Hacker News. There's no peer review here. The methodology is explained but not independently verified. The tasks used in the benchmark might happen to favor the 2B model's training distribution. Change the prompts, change the domain, and the results might flip. The 12B model almost certainly wins on tasks that require deep factual recall, complex reasoning chains, or domains where raw knowledge capacity matters. Legal documents, scientific literature, dense technical content. These are not the places where you'd expect a 2B model to hold the lead. Also, multi-turn coherence in a benchmark doesn't always translate to multi-turn coherence in production. Real users are messier than benchmark prompts. They change topics mid-conversation. They contradict themselves. They write in fragments. A controlled benchmark can look clean in ways that production never does. What surprised me was the reaction in the Hacker News comments. Engineers weren't dismissing this. Several people said they were switching their internal evaluation pipelines to test smaller models first, not as a budget move, but because results like this suggest the conventional wisdom is wrong often enough to be worth questioning. So what could this actually lead to? The practical implication is immediate. If you're building a multi-turn chatbot or an assistant that needs to hold a conversation over several exchanges, you should be benchmarking 2B and 3B models alongside the bigger ones. Not because small always wins, but because you now have evidence that it sometimes does. In exactly the use case you care about. For edge deployment, phones, embedded devices, local servers, this result is significant. A model that performs competitively on multi-turn tasks at 2B parameters can run on hardware that a 12B model can't touch. That opens up assistant-style applications in environments where you genuinely can't afford the compute. Longer term, this adds to a growing body of evidence that targeted training and architectural choices matter more than raw scale. Models like Phi 3, Mistral 7B, and now Gemma E2B keep punching above their weight class on specific tasks. The pattern is becoming hard to ignore. So why does this benchmark exist at all? Because the field has a scaling bias. Papers, leaderboards, and press releases default to bigger numbers. The assumption baked into most model selection decisions is that if you can afford the bigger model, you run the bigger model. Nobody gets fired for choosing the larger parameter count. But that assumption costs money, slows inference, and as this benchmark shows, is sometimes just wrong. Someone decided to actually test it instead of assuming. And the result is a data point that's now in the hands of every engineer who read that Hacker News post. The honest verdict? This is a single benchmark from a single source. Treat it as a strong hypothesis, not a proven fact. Run it yourself on your own data before making a model selection call. But do run it, because if it holds up in your use case, you just found a model that's faster, cheaper, and better at the thing you need. Next episode, we're looking at another open source project that's quietly replacing a paid API for a specific production task. And the cost difference is not small. Subscribe so you don't miss it.